Hey guys, this is the Academic Chemistry Chapter 8, Section 2, Part 3 notes. So we're still talking about building Lewis dot structures, but in this set of notes, we're going to talk about things that have charges. They're called polyatomic ions, and we're going to talk about what resonance is and also some expanded octets. So let's get started. So the first thing is polyatomic ions, and you're probably thinking, what the heck is a polyatomic ion? So let's go over the definition. So polyatomic ions are groups of atoms with a charge, and the prefix poly means many. So polyatomic means many atoms or a group of atoms, and an ion is anything with a charge. So it's a bunch of atoms covalently bonded together, but the overall structure has a charge. So you're going to follow the exact same steps you did with molecules. However, if it is an anion, as in if it is a polyatomic ion with a negative charge, then to have a negative charge, you had to gain electrons. So whatever the negative charge is, gained that many electrons. If it's -1, it gained 1 electron. If it's -2, it gained 2 electrons. If it's a cation, and a cation is a positively charged ion, then it lost electrons. So if it's a +1 overall charge, then you need to take away 1 electron from your total. If it's a +2 overall charge, you need to take away 2 from your total electrons. And then the entire structure is surrounded by brackets, and you put the charge as a superscript on the top right corner. So let's do an example. So first we're going to do ammonium. So ammonium is a nitrogen bonded to 4 hydrogens, so covalently bonded, but the overall structure in ammonium, not to be confused with ammonia, which is like what you clean with, ammonium has a charge to it. It has a +1 charge. So same exact thing we did with our covalent molecules. So first we have a nitrogen, so you find that on your periodic table. That has 5 valence electrons. Then you have a hydrogen. Each hydrogen has 1, but I have 4 of them. So I need to add those up, but you have to do something with your charge. So if you look here, I have a positive charge. Notice I don't see any numbers. When you don't see a number, you assume 1. So 1. Then you're going to do whatever the opposite of the charge is. So since this is a positive, I have to actually take away. And that's because electrons are negative. So to get an overall positive charge, you have to take away negative things. I know it's weird, but keep in mind we're tallying up negative charges. So to be positive, you have to subtract that. Or just remember, it's the opposite of whatever the charge is. So for a +1 charge, I need to take away 1 electron. So 5 plus 4 minus 1 is going to give us 8 overall electrons. And now we don't worry about the charges or anything like that. We do like we did before. So we put nitrogen in the center, and we're going to put all 4 hydrogens around it. And then we have 8 electrons to distribute. Remember, hydrogen is an exception. Hydrogen only wants 2 for its instead of octet, right? So those 2 have to be the bonding electrons. So there are our 8 electrons, and we've already distributed all 8 that we have. So I'm going to redraw it, and instead of the dots, I'm using straight lines. And then that last step that makes this a little different from your covalent compounds, those neutral ones we did before, you have to put brackets around it, and you have to put the charge. Do not forget that. That's a key one that students always forget. That way it quickly shows your reader this is a polyatomic ion. Let's do another example of a polyatomic ion. So this is hypochlorite. So this is a chlorine and an oxygen bound together, and they have an extra electron, which gives it that -1 charge. So same thing we've done before. Chlorine has 7 valence electrons. Oxygen has 6. I don't need to multiply either of these up because you don't see a subscript. So you know you only have 1 atom of each. So you're going to add those together. And then this negative charge, since I don't see a number, I can assume it's 1 and always do the opposite of the charge. So since it's a -1 charge, I'm actually going to add 1 to my total of electrons. So that's going to give me 14 electrons. I don't have a central atom because there's only 2 atoms, so they're just next to each other. You can pick whichever one you want to give your electrons to. I picked oxygens, 2, 4, 6, 8, 10, 12, 14. I've given out all the electrons I have. So this is the structure. If I look around, I notice I don't have to move anything around because everybody's octet is satisfied. Yay. So I'm just going to redraw it to make it nicer. And when I redraw it, the electrons in the center are going to be redrawn as a line. I'm almost done here, so it does take that extra step. Do not forget the extra step. Brackets and the charge. And then, boom, there is hypochlorite, all drawn for you. So the next thing we need to talk about is resonance. So resonance is when two or more Lewis structures can be drawn for the same molecule, and they're both correct. Just where do you pick? And when you have multiple ones, that's called resonance structure. So it arises from a double bond that moves between different points within the molecule. Sometimes that double bond will actually pop those electrons onto an atom as a lone pair in transition of going to another place to be the double bond. And here's a perfect example. So if you ever take organic chemistry, then benzene is going to be either your best friend or your enemy, depending how you like organic, but this is benzene. And if I look at my benzene on my left and I look at my benzene molecule on the right, you'll notice the double bonds aren't in the same spot. So for example, in the left molecule, this guy here, I've got double bonds, top right, bottom right, middle left. And if I look on this molecule, that's not where they are. So what happens is this double bond actually pushes over here, and then that pushes electrons here. And they keep moving, 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 that double bond. And if you remember the notes 8.2 part 1, I talked about that the bonds aren't taking up the same spot. You have a sigma bond, and then a pi bond is your second bond that kind of goes around the other bond. So the pi bond is kind of above the molecule, that second bond, so it can float around the molecule if other atoms can take on those electrons. So it doesn't actually stay in one place. So in nature, the molecules with resonance structures exist as a hybrid between all models. So this isn't actually what benzene ever looks like. This isn't what it looks like because those double bonds are just constantly swiveling around, 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 around. So we draw that as dotted lines. Now, for the scope of this course right now, you just need to be able to identify, oh, I could move some of these electrons around and make a different structure, and it's still going to follow all our Lewis dot rules, and that's going to be resonance. But you should know that none of those structures actually exist like that. It's not going to be stagnant like that, that those double bonds are constantly going back and forth. So let's draw one. Okay, so I've got sulfur dioxide. I'm going to do exactly what I've done before. Sulfur has 6, oxygen has 6. I've got 2 oxygens added up. No charges to worry about. This is just a molecule, not a polyatomic ion. So, okay, 18 electrons. Sulfur goes in the center, and I've got 2 oxygens, 1 on either side. So the first thing I'm going to do is give my oxygens, my outer atoms, their full octet. 2, 4, 6, 8. And then the other oxygen. 2, so 10, 12, 14, 16. I've got 2 more electrons, so they just go to sulfur. But if you notice, oxygens are all satisfied here, but sulfur isn't. Sulfur only has 6. So it needs 2 more electrons. So who's going to give a pair of electrons? It can't just be the left or just be the right. Either would work. So if I do this one, my left oxygen gives the electrons, then this oxygen kind of got gypped. So really, you could draw some arrows. So we're going to draw arrows in. So I want you to make sure you have this structure in your notes to start. And then your arrows show where electrons move. So my right side oxygen, these 2 electrons could also push over here. If these 2 came here, my sulfur would have too many, which means these 2 electrons need to come back this way. And there you go. You have 2 different structures. So it exists between the 2 of these. Both of these structures are totally possible. And notice on this structure, I could draw an arrow coming back here, electrons coming back here, and it works the same way. These structures go back and forth, so this is resonance, having both of these structures resonance structure. Now that I have these both drawn, I want to put them in brackets and then draw an arrow back and forth. And notice this arrow has like heads on either side, so it says it can be both of these. It goes back and forth between the 2, and that's what tells your reader both of these are possible structures. I've drawn the resonance. All right, let's do one more thing. So we're going to talk about expanded octet. And I talked about this definition already in notes. It means that an atom can take on more than 8 electrons. It happens when an atom is in the 3rd period or higher because it can add electrons to the D subshell on that outer energy level. So sulfur is notorious for this. Sulfur has the possibility of adding D electrons. So you do the exact same thing you did before. So sulfur has 6, fluorine has 7, you have 4 of them. So Add those up and you get 34. Sulfur goes in the center, put your fluorines on the outside, and then start giving away electrons to the fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, everyone's octet is satisfied, but you've got 2 more electrons. You only gave out 32, you've got 34, and then you remember sulfur is in the 3rd period or more, which means you can add 2 extra electrons to sulfur and it can handle it, and that's fine. And remember how forever I've been saying now you want to change to those lines for your bonds? You'll see why. This is really confusing and really sloppy. So I'm going to change it to this, which looks a lot nicer. It's clearer to see that sulfur, these are bonds here on sulfur, and this is a lone pair. That's it for polyatomic ions, resonance, and expanded octet. Make sure you talk to me if you have any questions during class, and otherwise I'll see you in the next set of notes. Okay, bye.